Dear audience, we talk about the radio waves of Earth orbiting satellites as well as geostationary satellites. This is the Earth here, Earth. This is the satellite. Orbiting around the Earth. The satellite is transmitting a radio wave that reaches or that covers this portion of the surface of the Earth. As the satellite moves in its orbit, the area covered by the beam of the satellite will move also along this path. This is a schematic of the satellite communication system. We have here mobile telephone users communicating with the satellite. We have uplink and downlink data or communication from the telephone to the satellite and from satellite to the telephone. Uplink from satellite, from telephone to satellite, and downlink from satellite to telephone. And in turn, the low Earth orbiting satellite is communicating with the gateway Earth station here, uplink and downlink. And the Earth station is connected to the public services telephone network. Communications can be effected using Earth orbiting satellites. Satellites are important because they can provide personal communications and long distance telephone and television circuits, digital communications, data transmission. And as we said, there are two types of satellites: geosynchronous orbiting satellites, geosynchronous orbits, where the satellite angular velocity is similar to the Earth's orbiter angular velocity, and the satellite will appear to be stationary with respect to the Earth, to an observer on the Earth. For the Earth orbiting satellite, on the other hand, the angular velocity of the satellite is greater than the angular velocity of an observer on the Earth, and the satellite will appear to be moving with respect to an observer on the Earth. Usually it moves faster than the Earth, than the angular velocity of the Earth. The satellites can reach remote areas that are unreachable by the terrestrial infrastructure, such as deserts, such as hard terrains that cannot be reached by cables or by towers. All orbits are essentially elliptical, with the Earth at one focus of the ellipse. Here we will derive equations for the speed of the satellite in the orbit and also for the time period of the satellite as it is orbiting around the Earth. Here is the satellite mass. R is the radius of the orbit. This is the orbit here. Let's draw it in a better way. Here, let's draw an orbit here. This is the orbit, and this is the Earth here. Assume it is at the center. We will assume here this is the Earth here at the center of the orbit, and the satellite is here, for example. orbiting around the Earth. The radius of the orbit is r, it is constant. Yeah. The radius is r. There are two forces acting in opposite directions on the satellite. The centrifugal force in this direction, away from the center of the orbit or orbital circle, and the gravitational force between the satellite and the Earth, pointing towards the center of the Earth. They should be equal for the satellite to be balanced, or for for constant radius, for the radius to be constant. If the centrifugal force is larger than the gravitational force, the R will be increasing, and if the gravitational force is greater than the centrifugal force, the radius will be decreasing. For the radius to be constant, the two forces should be equal. The gravitational force between the satellite and the Earth is given by this equation. Mu is Kepler's constant, 3.986 004418 kilometer cube per second squared, and m is the satellite mass in kilograms, r is the radius of the orbit, and here this equation gives the centrifugal force, v is the speed of the satellite, and r is the radius of the orbit. We can cancel m with here, and r with of the r's here, and v squared is equal to mu over r. V is equal to square root of mu over r. The period is the distance over speed. Distance of one complete round is 2 pi r, and v is taken from this equation. This is v. R will go here up, r to the power 1/2 times r is r to the power 1.5, 3 over 2, and 2 pi, and here root mu. This is the equation. There are two equations. One gives the speed of the satellite in the orbit, and the other gives the period, time period of one orbit for the satellite. As we mentioned, actual orbit is an ellipse, and the Earth is at one focus of the ellipse, and the radius or distance between the center of the Earth and the satellite is varying. It is not constant here. It is varying. If the satellite is here, the radius is this. The mean radius of the ellipse here is called RA, and the speed of the satellite is not constant. It depends on r, because r is not constant. Mu is Kepler's constant, r is the radius which is varying, and RA is the mean radius, constant. Now T is the same formula as this, but we replace r by capital R. That is here 2 pi capital R A instead of small r to the power 1.5 or square root of mu. An example here. This is the radius of the actual radius of the Earth, 6,378.14 kilometers, and let's consider this. This is almost approximately to scale. This is the Earth, and this is the orbit of the satellite. This distance here, from here to here, this distance called perigee. It is 1000 kilometers. And this distance from here to here, it is called apogee. It is 4000 kilometers. And this is the diameter of the Earth. It is twice the radius. So here we put RE is 6378 kilometers. HP here is 1000. HA is 4000. If you add these values, you obtain 603,378 times 2 to obtain the diameter of the Earth, plus 1000 plus 4000 plus 5000 equal 17756 kilometers. This is the major axis of the ellipse. The semi-major axis we divide by 2 to obtain the kept RA is 8878 kilometers. Now the period, the orbital period, is equal twice pi RA to the power 1.5 over square root of mu. Now this is RA to the power 1.5 equal times 2 times pi divided by mu under square root equal, it is 8325, as you can see, 83, because this 4.989, it's 5, 8325 second. We want to convert these seconds into hours and minutes and seconds, and I will show you how to do this. Now divide by 1 hour, which is 3600 seconds, and we obtain this value 2. We take the integer value, so it is 2 hours. Now we take the 2, okay, and multiply by 3600 to obtain the remaining seconds. We divide by 60 seconds for every 1 minute, and we obtain 18 minutes. You can see it's 18 minutes. We subtract the 18 minutes to obtain this and multiply by 60 to obtain the seconds, and this is around 45 seconds. So this is the how to convert seconds into hours, minutes and seconds, and we can convert it into days if the number is. Another example here, the Earth rotates once per side the real day. The period of rotation of the Earth around itself is 1 day, and 1 day is 23 hours 56 minutes and 4.09 seconds. Find the radius of the geostationary Earth orbiting satellite in kilometer. Now from this equation, T is given, the period of 1 day, and the mu is constant, pi is constant. We can find RA, the average RA. So from this equation, to get rid of this 1.5, we square this so that this will be RA to the power cubed, and this will be 2 pi squared is 4 pi squared. 2 pi, 2 times 2 is 4, and pi times pi is pi squared, and root mu times root mu is a mu. And RA cubed is equal to mu times t squared over 4 pi squared. Now t, we convert this into seconds as the following. It is easy to convert into seconds. 23 hours, each hour is 3600 seconds, plus 56 minutes, and each minute is 60 seconds plus the remaining seconds 4.09, and this is equal 86164.09 seconds. Now the period here squared, we square this, we multiply this by mu times u, okay, divided by 4 divided by pi divided by another pi, okay, and this will be Ra cubed. We take the cubic root to obtain the radius. I'll repeat this. T is 86164 86164.09 squared, okay, times mu divided by 4 times pi times pi, close this, and this is equal to this, and the cubic root, the answer is, as you can see, 42164, and here 42164, 0.169 kilometer. This is the answer, and this is the average orbital radius for geostationary satellite. 42,000 from the center of the Earth. If you want from the surface of the Earth, you subtract the radius of the Earth. Types of orbits. We have LEO, low Earth orbiting satellites, MEO, medium Earth orbiting satellites at a higher radius, and GEO, or geostationary orbit satellites at a higher radius also. And we have elliptical Earth orbit satellites, highly elliptical orbits. Now, typical numbers. Geosatellite height, not radius, height in kilometer, 35786.03 kilometers, and orbital velocity kilometer per second 3.0747 kilometer per second, and orbital period is 1 day, 23 hours 56 minutes and 4.1 seconds. MEO has a lower height, 10,255 kilometers, and velocity, higher velocity, 4.8954 kilometer per second, and the orbital period is lower, shorter than 1 day, because the satellite angular velocity is faster than the Earth, and the Earth will appear to be moving with respect to an observer on the Earth. So the period is 5 hours 55 minutes 48.4 seconds. LEO satellite is low Earth orbiting, low, 1,469 kilometer, lower than either of those, and the speed is larger, 7.1272 kilometer per second, and the period is is smaller, also 1 hour, only 50, around 2 hours. Another LEO, which is even at low altitude, it is 780 kilometer height above the Earth, and the speed is higher, 7.5 kilometer, around 7.5 kilometer per second, and the period is 1:40 minute 27. This is, as you can see, 7.5 kilometer per second is a huge speed. If you want to calculate this in kilometer per hour, let's calculate 7.4624 kilometer per second. Second is 1 over 3,600 seconds, 1 hour. 1 second is 1 over 3,600 hours. So we multiply by 3,600 600, and to obtain this. So this is the speed of the satellite in kilometer per hour. It is 26,864 kilometer per hour, over 25,000 kilometers per hour. The speed of the satellite. It is very, very huge speed. Here, if you want to obtain the height of the satellite, we subtract the Earth radius from the orbit radius. Okay. To attenuation calculations. The attenuation, the free space attenuation due to the spreading of the wave is given by this equation. It is lambda 4 pi r squared. Lambda is the wavelength, r is the distance between the satellite and the earth station, or distance between the transmitter and the receiver. Lambda equals c over f, and here we have 4 pi r. In dB we take 10 log, but because of this 2, it was 20. 10 log this is 20 log this without the square. So it's 20 log 4 pi fr. We put this in the numerator and this in the denominator to obtain positive value, because this will give negative values, this fraction. So this is the path loss in dB is 20 log 4 pi r f over. If we want to put f in megahertz and r in kilometer, we multiply by 10 to 6 so that f will be in megahertz, and multiply r by 10 to 3 in order for r to be in kilometer. And the speed of light is 3 times 10 to 8 meter per second. We gather the constant values and keep only the variable values will be f and r. So f and r variables, in f in kilometer and megahertz, and r in kilometer, and all these constants will add up to 32.44 dB. Other losses may involve the rainfall losses when the wave propagates from the satellite towards the earth, or vice versa, polarization mismatch, angular alignment of antennas, and so on. The system noise is given by this equation, kbtsb. kb is Boltzmann constant in joule per Kelvin, and T is system noise temperature in Kelvin, equivalent system noise temperature. B, the noise bandwidth in hertz, the frequency bandwidth. The carrier to noise ratio is the power received over the noise level. Satellite and earth, and this is the distance between the transmitter and receiver, or the receiver and transmitter. The power density is the power transmitted from the transmitter divided by a sphere with radius r. So the surface area of the sphere is 4 pi r squared, like this. When the transmitting antenna is here, is transmitting antenna, okay. The P transmitter will be distributed over this sphere with radius of r, and the power will be divided by the surface area. Power divided by the surface area, 4 pi r squared. But because of the gain of the antenna, the power will be concentrated in this direction. So we multiply by the gain of the antenna. This will the unit of this will be power per meter squared. This is the power density at the receiver. Now, to find the power received, we multiply the power density by the effective area of the receiver. Effective area is given by this equation, lambda squared over 4 pi times the gain of the receiver. Lambda is the wavelength. And PR is equal PT GT times GR over 4 pi squared r squared, 4 pi r all squared, and we take lambda here, divide by lambda to be squared. This is in watts. This value we call it IRP, PT times GT, transmitter power times the gain of the antenna of the transmitter is called effective isotropically radiated power. And GR is as it is, and this is the path loss. This is the free space path loss. If we have other losses, we add them to the free space loss. Any other losses. An example here. We have a satellite transmitting 10 watt, power of 10 watt, and gain of the antenna is 17 dB. So EIRP is 10 watt is 10 dB. 10 log 10, this here, 10 log 10 is equal 10, because log 10 is times 10 is equal 10. So the AIRP will be 17 plus 10 equal 27 dB. As you can see, it is 27 dB. And the distance between the satellite and the Earth station is 40,000 kilometers. The effective area of the receiver is 10 meters squared. Find the power density here. Find the P received. Okay. The power density is equal EIRP minus the loss, and also we have here an excess, assume losses in excess to free space loss of 10 dB. So we subtract the free space loss and the excess loss, 10 dB. So it is 27, EIRP was 27, 10 log, the distance is 40,000 kilometers, 4 times 10 to 7 squared, and we obtain the power density minus 146.03 dB, or if you convert it to a ratio, here we can convert it here to show you how to convert it, minus 146.03 negative sign, divide by 10 equal minus 14.603, and let's take 1 times exponential, not exponential, sorry, 1 10 to the power. Okay, where is 10 to the power? Here. Here, okay. Okay, it is 1 4 14.603 here, 14.603 negative sign, 10 to the power. It is here, the answer is 2.49, as you can see, 10 to minus 15 watt per meter square. We have converted the dB into ratio. The received power is equal the power density times the effective area, and dB we add, it will be addition. The received power was minus 146.03, and the effective area was 10 dB. It was given in the question. It was 10 dB. Here it is 10 meters. 10 log 10 is 10 also. 10 log 10 is 10. And this will be minus 136.03 dB. If we convert this again, let's convert it. You divide by 10, so you will get 136.03 minus divide by 10 and raise to the power 136.03 negative divide by 10 equal, and 10 to the power is equal here 2.49, 10 to minus 14 watts. Okay. If the gain of the receiver is 52.3, find P received. EIRP is 27 calculated, and G receiver is 52.3, and we have already calculated this, I remember maybe, and minus 10, we will obtain the same because it's the same problem. We have another example here. This is the Earth, and this is the effective radius of the Earth, because we are talking about waves here, and the wave is if you want the wave to be straight, moving in straight lines, then we use the effective radius. Compute the path attenuation in dB for low Earth orbiting satellite here with height of 780 kilometer. This height h is 707. This is 780 kilometer. H is 780 kilometer. This h, and the frequency is 1625 megahertz. The attenuation is given by this. F is equal to 20 log 4 pi r over lambda, free space attenuation, or by this equation in dB, 32.44 plus 20 log the frequency in megahertz times the distance. Here we already derived this equation. We have it here. This is the equation. Yes, this 32.44 plus 20 log F in megahertz and R in kilometer. So we use this equation. Okay, the frequency is the distance is 780 and the frequency is 1625, and we will get 154.5 dB attenuation. Another question within the same, another part of the question, calculate the path attenuation at zero elevation angle. This is the zero elevation angle on the satellite. This is the zero elevation angle because it's tangent to the Earth, to an observer here. The observer is here. This is the distance tangent to the Earth, and this, if you take, this is of course here, this 90 degrees, because this is tangent to the circle, this 90 degrees, and this distance from here to here is height, and this is the effective Earth radius. We have this equation, r squared is equal this squared minus this squared from Pythagoras theorem. This is ae plus h all squared minus ae squared. ae is 8497 kilometer plus h is 780 kilometer, and this is a. Under square root we will obtain this. We can verify this. 8497 plus 780 equal squared minus 8497 squared equal under square root. So the result is 3723.4 kilometer. Now once we find, once the distance is obtained, we put the distance in this equation here, this equation. So it's 32.44 plus 20 log. The distance now is here. We put this distance in kilometer, and the frequency is this here. On direct calculation we obtain the, if you want, 3723.4 times 1625 equal log times 20 plus 32.44, and this is equal to 168.07 dB, much greater than this because the distance is larger. We already defined the effective isotopically radiated power as the PT times GT, or in dB 10 log PT times GT, or PT in dB plus GT in dB. This is the elevation angle, and this is the Earth. Doppler shift, when the satellite transmits a signal towards an earth station and the satellite is moving, the frequency transmitted by the satellite will be a little bit different than the frequency received by the earth station due to the motion or the movement of the satellite. Ft is the true frequency of the satellite transmitter. Fr received frequency. They are slightly different. Vp phase velocity of the wave and Vt component of the transmitter velocity, the satellite velocity, directed towards the receiver. Here, you can see here. The satellite is moving in this direction. Okay. And this is towards the receiver. The receiver is here. Here is the receiver. Here is the antenna receiver here. So the component, the velocity of the satellite is Vs here, and the component of Vs towards the receiver is Vt. It's Vs times cosine theta. Okay. And lambda is the wavelength of the transmitted signal. Delta F is equal F received, frequency received, minus frequency transmitted. F received is greater than F transmitted when the transmitter is approaching the receiver, and the Fr is lower than the transmitted frequency if the transmitter is leaving the receiver. Now delta F over Ft, the frequency difference over the transmitted frequency, is equal the component of the satellite velocity towards the receiver over the phase velocity of the wave, and this is equal Vt over c. The speed of the wave is the speed of light. So delta F is equal Ft, you multiply, you take this here, Ft times Vt over c. You take Ft here, delta F equal Ft Vt over c here. Now Ft over c over Ft is lambda, so this is Vt over lambda, delta F. Example: a low Earth orbiting satellite is in circular orbit with height of 1000 kilometers. Transmitter frequency is 2.65 gigahertz. Find the velocity of SAT in orbit. Speed of SAT is equal square root of mu over r under square root, this Kepler constant. And the radius of the orbit is the height plus the radius of the Earth. This is like this. The Kepler constant divided by the radius of the orbit, so the radius of the Earth plus the orbit height, and this is the answer under square root to obtain the result. And this is the speed, 7.35 km per second, same as. Now the part B, find the component of velocity toward an observer at an Earth station as the satellite appears over horizon for an observer who is in the plane of the SAT orbit. As here, you can see here, Vt is equal Vs times cosine theta, and Vs is already calculated here, 7.35, and cosine theta is sine this angle. This angle is this over this. This is Re 7378 over this. This is 6378 plus 1000 here, and if you calculate this, it will be 7.35, okay, times 6378 divided by 6000 plus 1000, 7378, and this is equal to 6.35 km per second, or if you want in meter, multiply by 1000. You will get 6353.8, or it depends on the approximation here, meter per second. Now we want to find the Doppler shift. It is Vt over lambda. Here the equation is here. Vt over lambda. We already calculated Vt. It is 6353 here. This is Vt here. The wavelength, and here also. Here, sorry, we are. This is here. And the wavelength we can calculate it from the frequency, which is here 2.65 gigahertz. At this frequency the wavelength is 0.11321 meter. Lambda f equals c, so lambda is equal c over f. The result is 56.125 kilohertz. Right here, 63 divided by 0.11321, 0.11321, which is equal to here 56. This in hertz. If you want 10 kilohertz, divide by 1000 to obtain in kilohertz. We obtain 56.1 here, 56.125 kilohertz. The last part, if the frequency is 20 gigahertz, what's the wavelength? The data will be the same. We only change the wavelength corresponding to 20 gigahertz, where the wavelength is 1.5 centimeter, and the result will be 6353.8 divided by 0.015, and the result is, we divide by 1000 to obtain the result in kilohertz, and we obtain 423.6 kilohertz. This is the Doppler shift. Antennas used, you can see that an antenna, which a global antenna, covers large portion of the earth, and the spot beams, this here covers a spot, and this covers a certain spot. Multi-spot beams and the scanning beams, multi-spot beams, and you have vertical polarization and horizontal. The both antennas cover the same area, but with different polarizations. Measurements show that downtown urban area attenuation of satellite signal amounts to 16 dB, urban 13 dB, and suburban is 2 dB because it has less lower density of buildings and structures. This is the elevation angle. Polarization effects. The vertical component and horizontal component of the polarization will be affected differently due to buildings, and this will affect the received signal. For radio rotation or polarization, linear polarizations suffer from rotation through the ionosphere. The ionosphere is one of the layers of the atmosphere. In the presence of the Earth's magnetic field, the linear polarization will rotate, and this will affect the wave. And that's all for today. Thank you for listening. If you have any comments, any recommendations, any questions, please let me know. Thank you for listening.